In this video, we're going to be assessing the results of our refined model. So this is the model where we have just removed those four kind of model outlier observations that were violating our assumptions of normality and equal variance. And also what we should see after removing those four problematic observations is we should see an increase in those model performance metrics that we're using to assess how well our model is fitting the data. So some things to pay attention to. The first one is your model regression statistics table. So I've just taken these from the Excel workbook and pasted them into a PowerPoint slide. This is something similar you'll do for your final presentation. So we have our multiple R value. This value is increased. We'll look at a comparison on the next slide. Our adjusted R squared value also has increased slightly, and our standard error has also decreased. So those are the three things that we'd like to see from this regression statistics table: increase in multiple R, increase in adjusted R squared, and decrease in standard error. We can also see that our model overall is significant, which means that at least one of these predictors is useful in predicting the sale price of a house. But when we actually look at the p-values associated with each individual predictor, we see that they're all significant. And furthermore, we should see that the signs do make sense. As we increase the fireplaces of the house, the sale price increases. As we increase the overall quality of the house, the sale price on average increases. As we increase the square footage of the house, the sale price on average increases. And all of your dummy variables are in reference to the Brookdale and the Brookside reference variables. So remember, we had 5 neighborhoods left after reducing the categories, and then we have 4 dummy codes. So North Ames was the next most expensive neighborhood after Brookside. Then Crawford was the next more expensive after that. And then Somerset was the next more expensive after that, and Northridge was the most expensive neighborhood. So that's why you see those are also positive coefficients, and by different degrees depending on which neighborhood it was in. So that's how we kind of take this information and try to make sense of what's happening within our model. So now, and this also tells us, if this is the multiplier as we add one additional fireplace to the house. And this is the multiplier as we increase the rank by 1, and so on and so forth. And again, we'll take a look at that in more in depth when we actually do a prediction, because we're going to use these coefficients. These are the beta coefficients in our modeling equation that we're going to use to make a prediction in the very last part of this lab. So that's what you should be getting out of your tables. You can see a quick summary over here, and then also just trying to understand what's happening within this ANOVA table and this model table here. Okay, the next things that we want to assess are those assumptions that we were trying to make sure that we're not violating by removing those model outliers. Remember, we just removed 4 observations out of 1,521. So that's why you see 4 observations less here. You shouldn't see the same number of observations after you remove those. Okay. The next thing, again, that we are going to want to do is assess our residual plots. So for the residual plot specifically, we're assessing that model assumption of equal variance. So we can see that we don't have those kind of outliers that are floating out in space that are far away from the rest of the outlier values in each of these plots. We can see that for the most part, the values are constantly varied above and below that line of 0. And you can see in each of these plots, they're between -10 and 10. So kind of a consistent range above and below 0. And then we can also look to our normal probability plots over here. And Well, this normal probability plot is not perfectly straight. We would like to get this as straight as possible. We can see that the tails of the normal probability plot are not as pronounced. From the baseline model to this refined model, the residual values have shrunk quite a bit. The residual values in the baseline model, you can go back and check, are between negative 20 and 20. So we've by adding these useful predictors, we've reduced those residual values of the model, which was one of our goals, right, by a pretty significant amount. Now, we might be able to go through a little bit more refinement, maybe, taking in the residuals from like 8 to negative 8 or something like that. We do have to be careful, though, when we're doing things like that, that we don't overcorrect the data, or that we don't do so much manipulation that we build a model that fits our sample data well but doesn't generalize well to the population. So remember, we're ultimately what we're trying to do is we're going to use this model on unseen data to predict new outcomes to help this real estate company more accurately price homes in the boroughs where they sell their houses. So if you want to go through one more round of kind of pulling in the tails of that distribution, you can. You can also explore more variables. There's a number of iterations that we can do from here. But hopefully what you do see is that we are improving the model with each iteration, and also at the same time not trying to overcorrect the data or just build a model that fits our sample data again, but that doesn't generalize well to the population of data that we're going to be using this model to make predictions on. Okay, last little bit of model assessment is to compare the results of each model. So I am just looking at the model statistics table. Again, what we hope to see from model to model is an increase in that multiple R. If we look from the baseline to the full model, we see a pretty significant increase by about 0.22 in that correlation value. And then after we remove just those 4 observations, we see a little bit more of a lift in that multiple R squared. So with each iteration, we're seeing that increase in the multiple R squared, which is a good sign. Okay. Also, the adjusted R squared, again, this is the one that we use for comparison because it adjusts for the additional predictors that you add to the model. We see a significant lift from the baseline to the full model, and again, we haven't removed any observations yet. All we've done is just add more variables, more useful variables for prediction. So we can see with the baseline model, we could only explain 49.15% of the variation in the model, or the model captured 49.15% of the variation in sale price. When we move on to the to the full model, the adjusted R squared increases by over 35%. Okay, so we now have been able to explain 85.67% of the variation, or that's how much variation the model captures. And then even moving on to the refined model, again, where we've only removed those kind of 4 observations that were below negative 10 and above positive 10, right here in this residual plot, we see even a little bit more lift. So almost a % increase in the amount of variation that we can explain. So not significant, but we do see that improvement, and primarily we're making sure that we don't violate that equal variance assumption. Okay, and then comparing the standard error, well, we want to see increases in multiple R and increases in adjusted R squared. We want to see decreases in our standard error values. So we can see from model to model a significant decrease from baseline to full model just by adding those 3 additional predictors, and even a further decrease after we remove those 4 observations. The other thing that I will just want to draw your attention to, and I chose the living area square root variable residual plot because this is the one that is consistent throughout all the models. This is the only variable that's in the baseline model, but all we've done from model to model, again from baseline model to full model, is add more predictors, and you can see that equal variance assumption already starting to kind of balance out, with the exception of those outliers. Now, just removing those 4 outliers, we can see that they're no longer down in the plotting space. So at this point, again, you have more options if you want to pull in some of those outliers, again, some of those tails that we saw in the normal probability plot. We could, rein in those outlier values from 8 to -8 and see how, that affects the performance of our model. Again, the caveat is we want to be careful that we're not overcorrecting the data so that it overfits the sample and doesn't generalize well to the population. So it's a delicate balance in those things. So all that I'm really concerned about is that you guys are following the process and you're seeing improvements, and getting something out of how we use these tools in the real world to make better decisions.